Okay, so we have been looking at a bunch of series, right? So we looked at the Taylor series, then we looked at the Laurent series, which is typically defined about a point of non-analyticity, or a point which is centered in a non-analytic region, and then it has its own region or in which the series would be convergent. So let's look at the idea of convergence a little more closely in this lecture. Okay, so we collect together a few statements, not necessarily trying to provide any rigorous proof or anything, but these are all, well-established arguments. So our goal will be to assimilate, these various different facts associated with Taylor series and convergence associated with them, and we wish to be aware of these so that we know, where these things hold and when they may run into difficulties, right? So that's the philosophy. So if a function is represented by a Taylor series of this form, so suppose we just know the Taylor series of some function, and then we happen to know that this converges at some point z1 other than z equal to z0. Of course, if there is a Taylor series of this form, and if it's a valid Taylor series, then it must definitely converge at z0. And if we happen to know that there is some other point z0 at which it also converges, then it's possible to show that in fact this series is absolutely convergent, not just convergent, but absolutely convergent. Absolutely convergent simply means that in place of these, so you can think of these as a bunch of complex numbers which are being added, but in place of these different complex numbers which are being added, you simply replace each of these terms in your series expansion by that absolute value, right? Even that is going to converge at every point that lies in the interior of this region, which is defined by this circle centered about z0 and whose radius is mod of z1 minus z0, right? So that's a theorem which says that it's all, and it's not very difficult to prove. I mean, you can show that it's there is a certain series of involving real numbers really. So when you take modulus of this, then you can argue that this is a convergent series, the absolute the sum of the absolute values whenever z lies between, it lies within the circle defined by z1, right? So but we will not go into the details of this argument, but basically it's true, right? So what it boils down to is, if you are given a Taylor series about some point, and if there is another point z1 which is some distance away from it, then for sure, in this entire region which is interior to this, you're guaranteed that this Taylor series will converge. And closely associated with this is the concept of the circle of convergence, right? So this is defined as the greatest circle around z0 such that the series converges at each point inside. So given that you have a Taylor series which is well defined at a point, for sure it's well defined in some circle of convergence. So maybe a small circle or a big circle, and it may be even a circle with radius infinite. So the radius of the circle of convergence is called radius of convergence, right? And it could be infinite, which is the case when you have entire functions. We have seen that entire functions, a classic example is of course e to the z. Now e to the z has this expansion which is valid about any point. Let's say you're looking at it about the origin, then this expansion will converge no matter what value of z you take, any finite value of z, and it is going to converge, right? But on the other hand, if you look at other kinds of functions, we will look at some examples where there is going to be a finite radius of convergence, finite circle of convergence. And if that happens, then typically there is going to be a singularity sitting on this circle, right? It could be one singularity, it could be more singularities, right? But there's at least a singularity sitting there. And what this tells you is that the definition of the circle of convergence, along with this idea that if you can find any point z1 where it is convergent, then all the entire region interior to that is also convergent, means that if there is a circle of, if you have found the circle of convergence, then for sure any point outside the circle of convergence will not be a convergent point for this series, because if it is, then by this theorem, then it would mean that, you know, that will become the radius of convergence, not something less than that, right? Because of this fact which we just stated. So there is a circle of convergence, and any point outside the circle of convergence cannot be a convergent point, right? So then there is another idea which is, of great importance, and that is the idea of uniform convergence, right? So again, we will not go into giving any rigorous proofs or anything of this kind. So the idea of uniform convergence is basically that, if you take a whole region in which your Taylor series is convergent, you have a series of this kind, and it's convergent in this entire region, mod of z minus z naught less than 1. Now, if you take any neighboring points, basically the series will converge in pretty much the same manner at any two neighboring points. That's a very crude way of saying it. But basically what essentially it means is, you can think of, this function s of z. It's a continuous function. The idea of convergence of a series is that, subsequent terms should become lower and lower, and then they should zero in on a certain value. So you should be able to find, given any, if you're saying that this series at a point z converges to a value s of z, then you should be able to get as close as you want to this point by choosing a term truncation of this term, which is sufficiently large. So what the idea of uniform convergence means is that, given that you want s of z to be close to the value, you have given a certain spread around this s of z at a certain point, and if you give the same spread at a neighboring point, right, it's enough to truncate the series at the same n in both of these cases, basically. I mean, that's a crude way I'm putting it. I'm not going to give you the details, but essentially what it means is, this function, this kind of a series is going to give you a continuous function. S of z is a continuous function, and in fact it's more than continuous. It's analytic at everywhere inside the circle of convergence, and that has important consequences, because then you can take the derivative of such a function. You can work with contour integral, sort of term by term, and all this. We will discuss this as we go along, but for now, we are stating these as facts, and let's look at an example to illustrate how this works out. So suppose you consider a function like e to the z minus 1 over z, right? So this function clearly has some mess sitting at z equal to 0, and so at exactly z equal to 0, you define this function to be 1, and this function to be e to the z minus 1 over z everywhere else. So now it turns out that this function, which appeared to have a singularity at z equal to 0, has actually been cured of the singularity. You say that there is a removable singularity, and that singularity has been removed, right? So it turns out that, in fact, this function defined this manner is actually an entire function, as can be seen by writing down this series representation, and then just using the arguments which we just presented earlier, right? So first thing to do is to just expand e to the z itself, which we know how to do, and then e to the z minus 1 will turn out to be just summation over n, going from 1 to infinity z to the n over n factorial. And so then if you divide this whole thing by z, then you get another series where the series starts from 1, right? So e to the z minus 1 over z is the series 1 plus z over 2 factorial plus z squared over 3 factorial, so on. Now we see that this series on the right hand side seems to have no difficulties at z equal to 0. On the other hand, if you blindly try to compute the value on the left hand side, we run into difficulties. But so if we assign the value of this function to be exactly the limit to which this series expansion on the right hand side is going to at z equal to 0, then basically there is no issue. You have cured the singularity, and this series, in fact, you sort of define this value of this function at that point using this series itself. right? So this series, and then we argue that if you have a Taylor series of this form, or you know, so in this case it's it starts from 1, so it's there's a constant term plus z over 2 factorial so on. If you have a Taylor series or a Maclaurin series, uh, that is the value of this function at that point, right? So we have just seen that this function is going to be convergent uh, at all points interior to this, the circle of interior to the region defined by this radius of convergence. Okay, so the essential idea is that there are these kinds of singularities which can be cured, just by using the series expansion and then arguing that the series is convergent there. So there is a well-defined limit, and so you can actually take a derivative which it's analytic. All the nice properties of analyticity will hold at every point, which can be checked. Okay, so similar results will hold also for Laurent series expansions, right? So far we considered Taylor series expansions, but in fact, if you have a series of this kind where you have powers in 1 over z minus z naught, those two have similar results. So the reason is that you can actually think of 1 over z minus z naught as some other complex number w, and so basically you are working with a series of this kind, bn w to the n, where n goes from 1 to infinity, and so this is really like a Taylor series in w. And so then we would argue that this has its own circle of convergence, so region of convergence, and it has a certain radius of convergence, which suppose we find out that its radius of convergence is small r, then we are assured that this series is going to be convergent whenever mod of w is less than r. But what is meant by mod of w being less than r? It's the same as saying mod of 1 over z minus z naught is less than r, which is the same as saying mod of z minus z naught is greater than r. So that's why, so whatever results seem to hold and inside a region of convergence, or in the interior of a circle of convergence, a similar type of story holds for series of this kind, except now you must say that the region is exterior to this circle. And so in fact, if you stitch together terms of this kind, and then you make a Laurent series, you take terms of this kind and then terms of this kind, and then there is a region of convergence for this series. So mod of z minus z naught must be less than capital R. As far as this series is concerned, if it has to be convergent, R must be less than mod of z minus z naught. So mod of z minus z naught must lie outside small r. Now therefore, if you want to have an annular region, well-defined annular region, then it better be that the small r is less than capital R. Otherwise, if it happens that small r is greater than capital R, then such a series would be nowhere convergent. If you artificially try to bring together, one series of this kind and another series of this kind, and try to make an overall series, you may actually end up with an overall series, Laurent series, which is not convergent anywhere. So let's quickly look at one example of this kind. So we know that this series 1 plus z squared so on is convergent whenever mod z is less than 1. On the other hand, the series 1 plus 2 over z plus 2 over z the whole squared so on is convergent whenever mod of 2 by z is less than 1. In other words, mod z is greater than 2, right? So that means the small r in this case is 2 and large R in this case is actually 1. So there is no region where, if you just add these two series together, there is nowhere that simultaneously both of these will converge. So overall, this is a Laurent series which has no region of convergence. Okay, so that's all for this lecture. Thank you.